Let's dive right into this explainer, because we're looking at a mind-bending rule of the universe today. We are going to explore why the perfectly ordinary act of copy-pasting is physically impossible in the quantum world. I mean, think about how ingrained copy-pasting is in our daily routines. You probably hit Control-C and Control-V dozens of times a day without a second thought. But, and this should completely rattle you, in the quantum world, copy-paste simply does not exist. You literally cannot duplicate an unknown qubit. And it's not because our tech isn't advanced enough yet or we're missing the right tools. It's because the universe fundamentally forbids it.
What's really fascinating here is the stark contrast between our everyday digital lives and the strict, unyielding reality of a quantum bit. In the classical world, your computer is copying files a billion times a second. Photos, songs, whole movies, they're duplicated perfectly, endlessly, and basically for free. Copying is the absolute core of what information machines do, right? So why would a qubit, the quantum version of a regular bit, be governed by totally different rules? Why is duplicating it universally forbidden?
Well, before we get into the why, we really need to understand the massive stakes here. This isn't just some quirky little footnote in an advanced physics textbook. The fact that you cannot copy a qubit is the foundational law making future quantum technology secure. It is the exact reason why quantum encryption actually works. It's the reason a future quantum banknote would be physically impossible to counterfeit. And it's the hidden rule dictating how we even have to build quantum computers in the first place. You can't just back up your work halfway through a quantum calculation like saving a Word doc. It's a fundamental law called the no-cloning theorem. And once you see why it's true, all this futuristic tech suddenly makes perfect sense.
To make this easy, we're going to break down this no-cloning theorem into three simple ideas: observation destroys, the deep rules, and finally, a quantum superpower. Okay, idea one. Observation destroys, meaning to copy something, you first have to look at it. Think about a standard office photocopier. It has to shine a bright light and actively read a page before it can ever print a duplicate. To copy anything, you must first observe it. There's absolutely no way around that. You can't reproduce what you haven't examined. Now, in our everyday world, that's fine. But in the quantum world, observation is a highly destructive act.
The crucial point to remember is that unlike a regular bit, a qubit exists in this incredibly fragile state of superposition. A regular bit is just a plain 0 or a 1. You can peek at it as many times as you want without disturbing it. But a qubit, it holds a delicate mixture of both possibilities, a 0 and a 1, weighted together in a really precise, beautiful way. But here's the catch. The very instant you look at it to measure it, that rich mixture completely shatters. You don't get the blend back, you just get a plain, single answer, a 0 or a 1. The instant you look, all that subtle in-between information is gone forever.
Actually, here is my favorite way to visualize this. Picture trying to photocopy a soap bubble. Imagine this beautiful, shimmering, three-dimensional bubble full of swirling colors. To copy it, you'd have to grab it and lay it flat on the copier glass. And the second your fingers touch it, pop. You're left holding a wet smear, not a bubble. The simple act of grabbing that bubble to capture it destroys the exact thing you wanted to read. And that is exactly what happens to a qubit. Reading it destroys it. Which means you can never get a faithful look at the original. Which means you can never make a faithful copy. One observation, one collapsed answer, and the original is changed forever.
Moving to idea 2, the deep rules. This is where we see that the math itself won't allow blind copying. Because inevitably, a skeptic is going to ask a very clever question. Well, what if a magic machine could just blindly copy a qubit without looking at it? You know, no measurement, no collapsing the bubble. Just pure, blind duplication. This part will really bend your brain, because even that magic machine is impossible, and we can actually prove it without ever having to build a thing.
The reason lives in a very deep feature of quantum rules. Basically, quantum rules are incredibly gentle and proportional. Physicists call this linearity. But let's just focus on how it actually behaves. Whatever a quantum machine does to a pure note, like a pure 0 or a pure 1, it absolutely must do to any blend of them in the exact same proportions. The machine can't have one behavior for pure tones and then some sneakier, totally different behavior for blends. It has to treat the blend as exactly that, a blend. So if you demand a universal copier, it faces an impossible task. When you feed it a mixture, this proportional rule forces it to tangle the two qubits together into a locked fate, rather than producing two clean, independent copies.
See, to copy the pure notes, the machine has to behave one way. To copy the blends, it would have to behave in an entirely different way. And no single machine can do both. The contradiction is baked right into the math itself, completely forbidding the copying of an unknown qubit.
It is literally as mathematically impossible as a triangle with 4 sides. Though I should point out the word unknown here. If you already know the qubit's exact recipe written down somewhere, yeah, of course, you can easily make 1,000 of them just by following the recipe. The no-cloning theorem only forbids copying a qubit whose recipe you don't have straight from the physical copy in front of you. Basically, you cannot copy what you don't know.
All right, idea 3, a quantum superpower, when a limitation becomes an unbreakable lock. Because here is where everything flips. What sounds like a massive, frustrating restriction is actually the ultimate gift for security. We are taking a limitation and turning it into an absolute superpower.
Imagine you're sending a top-secret message across the world, encoded in qubits. Eve the spy taps the line. Her goal is to copy your message, pass the original along to you so you don't notice, and read her copy in secret. I mean, that's how normal wiretapping works, right? Silent, perfect copies, but these are qubits. Because Eve cannot copy the data, remember, the universe won't let her build that machine, she's forced to measure it. And measuring, just like with our soap bubble, shatters the delicate blend and completely mangles the original message. So when your message finally arrives to you, it's visibly disturbed. The damage itself acts as an alarm bell. Physics guarantees she leaves undeniable fingerprints.
This mathematical impossibility is the exact foundation of quantum cryptography. A spy who tries to copy gets absolutely nothing useful, and they trip the alarm at the exact same time. The exact same logic guarantees that future quantum money will be literally uncounterfeitable, because a forger cannot duplicate the quantum tokens hidden inside a genuine note. So, no cloning isn't a wall blocking our progress, it's a lock that cannot be picked. It guarantees our deepest secrets can never be stolen without leaving a trace.
So let's quickly recap our 3 big ideas here. First, copying requires reading, but reading an unknown qubit pops that delicate bubble. Second, the math itself strictly forbids the blind cloning of unknown blends because quantum rules demand proportional treatment. And third, this very impossibility creates an unbreakable lock for our secrets, turning a limitation into an incredible security superpower.
But before we wrap this explainer up, I have a mind-bending scientific trick that should probably keep you up tonight. Scientists have this trick called quantum teleportation. It's entirely real. A qubit's exact state vanishes from one place and reappears perfectly somewhere far away. It is literally moved across space. But wait, how on earth does that not violate everything we just proved today?
If you can't copy a qubit, how can you possibly send one across the room or across the world? Teleportation somehow moves a qubit without ever copying it. So what's your guess for the trick? How do you think they do it? Drop your guesses in the comments below because we're going to explore that beautiful, sneaky answer next time. Thanks for joining me on this explainer and keep questioning the universe.